So first thing, you need to know that your diameter is the longest chord. It divides the circle into two equal semicircles or two equal parts. So it has got its own theorem. Okay? So according to theorem 3, right, an angle subtended by diameter, okay, is a right angle. Now the angle must be at the circumference. So an angle subtended by diameter at the circumference is a right angle. Right, so if you have a circle, I've got nice circles here. Right, so if you have a circle like that, I will approximate it. Okay. So if say you've got a center somewhere there, I will approximate it. I've got a very eyesight by the way. Okay. So if you draw a line like that, okay, it's not a straight line, it's not perfect, right? I hope you know that the angle along a straight line is equal to what? 180 degrees, right? So if I join this point to another point on the circumference, and then I draw another line from there, right? So this is our diameter. You stop talking. That's our diameter. The angle here is 180 degrees. It's an angle at the what? Center. So theorem 3, which is based on the diameter, it originates from theorem 2. So we have an angle at the center here, which is 180. It's 2 times an angle at the what? Circumference. Which means you divide 180 by what? By 2. Then you get your 90-degree angle. Okay. Now the acceptable reason, okay, the acceptable reason is to say angle in a semicircle. Please, it's one angle, it's singular. You don't say angles in a semicircle, no. It's an angle in a semicircle. So this is the acceptable reason. So an angle which is subtended by a diameter at the circumference is equal to 90 degrees. The acceptable reason, angle in a semicircle. Please take note, it is singular. It's not plural. You can't say angles, it's one. Alright? So, as long as you've got a diameter and you see that there's an angle at the circumference which is subtended by the diameter, that angle will always be equal to 90 degrees. Okay? Then, this theorem has got its converse, because sometimes you may be asked to prove that a line is a diameter. So you do the opposite now. If a line is a diameter, all you have to do is prove that the angle that is subtended by the line is equal to 90 degrees. Okay? So the acceptable reason for the converse, you just write chord subtends 90-degree angle, or just write 90 degrees. Okay? If you put line here as well, where there is chord, because a chord is a line, so if you put line subtends 90-degree angle, that is also acceptable. Okay, so the converse, chord subtends 90 degrees. Now, with the converse, you won't be told that the line is a diameter. Okay, but you'll be supposed to prove that the line is a what? Is a diameter. So it will be the opposite of the original theorem. So if the angle subtended by a chord at a point on the circle, please be aware that by this phrase here, point on the circle, we are referring to the circumference. Okay? So that's the circumference. Okay, is 90 degrees, then the chord is a diameter. Alright? So as long as the chord subtends an angle which is equal to 90 degrees, you can conclude that therefore the line which subtends that angle is a diameter. Okay? So that's theorem 3 and the converse. Okay, theorem 4, it is a center theorem because it is related to theorem 2. So theorem 2 is like the mother. Theorem 3 and theorem 4, they originate from theorem 2. Okay, so according to theorem 4, an arc or a chord, okay, subtends equal angles at the circumference of the circle. Okay, an arc or a chord subtends equal angles at the what? Circumference of the circle. What this means is, if you draw a chord, right, then you create two angles at the circumference like this. Okay, this one now is not at the circumference. So if I extend, okay, by the way, I used this to explain the other case. Right? So if you have got two angles, like this angle and that angle, as long as those angles are at the circumference, okay, and they are subtended by the same chord or same arc, then you can conclude that they are equal. Okay, so if this is x, that will also be x. Please take note, both angles must be at the circumference. Okay, and they must be in the same segment. Okay, remember this chord here, it will divide the circle into two segments. So you have your major segment and your minor segment. So both angles must be at the circumference and they must be in the same segment. And they have to be subtended by the same chord or by the same arc. Okay? Now the acceptable reason for that is this one here. You write angles in the same segment. That's the acceptable reason according to your the examination guidelines for 2021. Okay? Now, I'm sure you can see here that we have got what's called a butterfly. So this is the butterfly. So whenever you see a butterfly like that, you must remember that that's theorem 4. Okay? So, with that butterfly, this angle will be equal to that, and that angle will also be equal to that angle. The angles can only be equal if both are at the circumference. If one of them is not, then you can't use theorem 4. So if one of them is inside the circle, or if both of them are inside the circle, you cannot say they are equal. They can only be equal if they are both at the circumference. Okay? Right? Now, the proof of this, it's not examinable, but it comes from Theorem 2. You have to do a construction where, in this case, if you are given a center, or here you join point A to point O and join point B to point O, so that you create this triangle. You create, not triangle, such that you create this shape. Right? That one there. So that this angle here is going to be an angle at the center. So it will be 2 times that. And this same angle here, it will also be 2 times this angle. Remember, there are 3 diagrams for Theorem 2. There are 3 I hope you drew those 3 diagrams. So, based on Theorem 2, if this is an angle at the center, and there is a common chord here called AB, this chord subtends this angle C, this chord subtends angle D at the circumference. So both angle D and angle C, they are half of the obtuse angle at the center. Okay? But unfortunately, the proof is not examinable. This is not an examinable proof, so I'm not worried much about it. You can read on your own, but you need to know that it originates from Theorem 2. Okay, so this one here, if you see a butterfly, Theorem 4, angles in the same segment. Okay.